All right, so another example. Finding the integral from negative infinity to infinity of 1 over x squared plus 1. So this is the graph of 1 over x squared plus 1. So we're supposed to start at negative infinity and go all the way to positive infinity. So we're supposed to find all this area under the curve. So what we can do this time is we can just do this integral in two pieces. So we can find that area under the curve. That'll be the integral from 0 to infinity of 1 over x squared plus 1. And we can find this area under the curve. That will be the integral from negative infinity to 0 of 1 over x squared plus 1. All right. Now it turns out you could just say, okay, well, by symmetry, this area is going to be equal to that area. So you could just compute this integral and double it. But you can't always do that on problems, I mean, if you don't have the symmetry going on. So we're just going to compute this integral in two pieces. Now, you might say, well, why did you break this up by going to 0? Like, why didn't you do, for instance, why didn't you split this up as the integral from negative infinity to 7? And then why didn't you add on the integral from 7 to infinity? So why did you pick 0 as your stopping point? So why didn't you just pick 7? Like, why didn't you take the area up to 7 and then do the area under the curve from after 7, from 7 to infinity? Well, you could have. It doesn't matter. So when you're computing an improper integral of this form, your starting and stopping point for your bounds here doesn't matter. You can pick them whatever you want them to be. So, right, if either of these integrals, when you make your choice, ever isn't a finite number, in other words, if one of the integrals ever diverges, then we just say the integral is divergent. So it doesn't converge to a finite number. So, all right, so we want to compute this integral. So we said, okay, we'll break it up into two integrals. The integral from negative infinity to 0 of 1 over x squared plus 1, and the integral from 0 to infinity of 1 over x squared plus 1. Okay? So we're going to say, well, what happens when we take more and more area going this way? If we take more and more area going this way, do we get a finite number? So we're going to take the limit as b goes to negative infinity of the integral b to 0 of 1 over x squared plus 1. And over here for this integral, we're going to say what happens is we take more and more area going this way. In other words, what happens as we take the limit, we'll do the limit as c goes to infinity of the integral from 0 to c of 1 over x squared plus 1 dx. Okay. Now an antiderivative of 1 over x squared plus 1, you can do tan inverse. So we're supposed to plug in 0, plug in b, and subtract. Same thing over here. So we're supposed to plug in c, plug in 0, and subtract. So we're finding the limit as b goes to negative infinity of tan inverse of 0 minus tan inverse of b plus the limit as c goes to infinity of tan inverse of c minus tan inverse of 0. All right, well, tan inverse of 0 is 0. You're looking for an angle with a tangent value of 0 between negative pi over 2 and pi over 2. Well, that's going to be 0. So that guy's 0. We got that guy covered. Now, what about this limit? What happens as b goes to negative infinity of tan inverse of b? Or in other words, arctangent to b. Well, remember, I said I want you to be able to draw the graph of tan inverse, or arctangent. In other words, arctangent. Same thing. So I said sometimes it'll help you out. Well, here's one of those scenarios where it'll help you out. Here is a graph of tan inverse. You got horizontal asymptotes of pi over 2 y equals negative pi over 2. The graph of tan inverse looks like this. Okay, so we got to say, well, what happens as b approaches negative infinity of tan inverse of b? So what happens as you plug in bigger and bigger negative numbers into here? Technically, it's smaller and smaller negative numbers, but numbers that become more and more negative. Well, if you plug in numbers that become more and more negative into tan inverse, you're traveling this way. Tan inverse is spitting out numbers that are getting closer and closer to negative pi over 2. So as you travel this way, you get closer and closer to negative pi over 2. So the limit as b goes to a negative infinity of tan inverse of b is negative pi over 2. So we have negative pi over 2 there. In other words, positive pi over 2. Now over here, we have to say, well, what's the limit as c goes to infinity of tan inverse of c? Okay, if you plug in bigger and bigger numbers into tan inverse, as you travel this way, tan inverse is going to spit out numbers closer and closer to pi over 2. So the limit as c goes to infinity of tan inverse of c is pi over 2. And tan inverse of 0 is 0. So we get a negative pi over 2, which is pi over 2 plus pi over 2. That gives you pi. So there we go, pi. This area under the curve, total area under the curve, is pi.